Good morning all. This is Dr. T.P. Lakshmi, working as an assistant professor in the Department of Computer Science and Engineering. Already we seen some algorithms which is in the distributed mutual exclusion, and last class we seen those algorithm, that is a central server algorithm, ring based algorithm, multicasting. So these are the algorithms that we seen. Today that we are going to be see about the algorithm on elections. Okay, so you already know about the meaning of the word elections. So this figure represents like a voting. Like elections means what? Just like a voting and choosing a leader, right? So same thing, while choosing the coordinator to enter into the critical section, we need an election. So for that we have two algorithms here. Okay, one is a ring based algorithm and another is Bully algorithm. So we'll see one by one. So before moving on to this, we should see the introduction of what is election algorithm that we need to be know. For the election, the algorithm for choosing a unique process to play a particular role is called as an election algorithm. Okay, so you know that what is critical section. Okay, the data which is shared, which is need to be shared by, which is going to be accessed by more than one process, that type of data that we are keeping in a critical section. Okay, and we seen some requirements also. Those three requirements, the first three requirements should be satisfied always. Okay, but the third one is not mandatory, it is optional only. The first one is safety, that means only one process should enter into the critical section at the time. And the next one is liveness, that means for enter into the critical section or any process wants to exit from the critical section, they need to send the request to the the remaining process in the remaining process, or the leader will be there. For example, if you take a central server algorithm, we the server is and plays a leader there, so it plays a single role, that is a leader role. So they, whatever process they wants to enter into the critical section or they want to leave the critical section, they should send the response message and the request message to the server. Okay, that only we seen still. But here the election, I already told you that an algorithm for choosing a unique, we'll see what are the topics that we are going to be covered. Okay, the first one is introduction part, and the next one is, I told you right, two algorithms. One is first we are going to be see about the introduction of this election algorithm. Next one is the ring based algorithm, and third one is the Bully algorithm. Using a unique process for the particular role. Okay, it is an algorithm, that is an election algorithm. It's nothing but, I told you right, it is going to be chosen unique process, that means one process for play a particular role. Okay, for example, we seen that server in the distributed mutex. In the central server algorithm, we seen the server as plays a role for getting the giving the response to the client, whoever sending the request to enter into the critical section. The same like here, for example, the server in the distributed mutex is an example for this one. Okay, and each process can call only one election. For example, if we have 5 processes in that, okay, only one time only they should call an election. Each process should call the election only one time. Okay, and multiple concurrent elections can be called by the different process. Sometimes multiple concurrently they can, more than one process can call the elections. Okay, that time what we should know now, based upon the algorithm, that we need to be choose a coordinator. Okay, if concurrently more than one process is going to be, start the election. Okay, call the election. Okay, and the participant, here we have two concepts. One is participant and another one is non-participant. Okay, participant means the process is going to be engaged in an election. Non-participant means they are not going to be involved in an elections. Okay, that you know, like generally what we can say that the election, the person who is going to be put the vote for the vote, that we can say that persons are participants. The persons who are not ready to vote, then we can say those persons are non-participants. Okay, then who will be win here? Generally in the election, who will be win? Who is getting the majority of vote, right? The same thing, the process with the largest ID only wins here. The selection algorithm, the process with the largest ID, who is getting the largest, the process who is going to get more number of responses that with the from the process, then we can say that process is a winner here. And election algorithm also, we need a choice actually. That means the election algorithm is needed for this choice is nothing but it is essential for all the process agrees on the choice. If any of the election algorithm process, if they are giving any choice, okay, for example, if they are giving any office, right, then all the process can utilize it. Okay, that is an main thing here. And we can say that the process calls the algorithm, it takes an action that initiates a particular run on the election algorithm. Each process PI has a variable elected. Okay, initially each process that is a PI has a variable elected I is equal to null. Okay, that means it is not elected, each process or initially it is 0. Okay. Then after, that means they don't know each for example, if we have 5 process P1, P2, P3, P5, all are not elected. Just it's simply we have 5 processes in the system. Okay, they are going to be, these 5 are going to be entered into the critical section. So in that initially all are null and no other process knows that who elected first initially. Okay, they don't know each other. First one is E1. Okay, E1 means safety, that you know. A participant process PI as elected. The participant process PI as elected. First, if the participant PI has 2 options, one is elected is equal to not yet defined or elected of I. PI means it is elected suffix I. So this is also suffix I only. Of a participant process must be P max, elected process which is having the largest ID. Okay, when the process can be elected which is getting the largest ID. Okay, so initially the participant process PI, either it is having the 2 values, that is this one, okay, that is not yet defined, or elected of I is equal to P. Elected of I is equal to P, where P, what do you mean by P? It is nothing but chosen as the non-crashed process. It is nothing but chosen as the non-crashed process. Okay, at the end of the run with the largest identifier. At the end of the election with the, run with the largest identifier. Next one is liveness. That means here also we can say, I told you right, safety means what? Only one process can enter into the critical section, right? Here also only one process is going to be elected. Okay, only one process is going to be elected and that process is going to be with the largest ID. Okay, that is which is having the largest, which is going to get the having the largest ID, that process is going to be elected, right? So that is what safety here. So this one is satisfied. Next one is liveness. What do you mean by liveness? All process participate and eventually set elected. I is not equal to crash. Okay, all process PI participate and eventually either set I is not equal to this one, this symbol. I told you right, special symbol. That means not yet defined, or we can say it is crash. Okay, either it is not equal to defined. That means the process participate or eventually elected, the whatever process which is going to be participate in that, and it is selected, it is elected also, eventually it is set as the elected of I should not, it is not equal to, okay, not yet defined or crash. So this also should be satisfied. Okay, why? Because it is asking the request, right? The process needs to be entered into the critical section or going to be exit from the critical section. Okay, so it is asking the remaining n-1 process in the system, right? Then only they are going to be enter or exit. Okay, now next one we'll see the performance. First here the performance is based on we should take care of the bandwidth consumption. Okay, that means the total network bandwidth utilization is directly proportional to the number of message sent. So you should take care. They are directly proportional to the number of message sent. Okay, the network of the bandwidth consumption is directly proportional to the number of messages sent. Next, what do you mean by turnaround time? I think you studied in the OS. What do you mean by turnaround time? The number of serialized messages, what do you mean by turnaround time? The number of serialization messages transmitted, the times between the initiation and the termination of the single run. The time taken between the initialization and the termination of the single run. So these two should be taken care of in the election algorithm. Next, a ring-based algorithm. What do you mean by, already we seen this one in the distributed mutual exclusion, right? So again we will see the same ring-based algorithm in the election algorithm. It will be based on the election algorithm. It was developed in the year of 1979. It was it was developed by Chang and the Roberts in the year of Chang and the Roberts in the year of 1979, a ring-based algorithm. Okay, so this one we already seen in the mutual exclusion how it will be work. Okay, the simple procedure. First, it will be arranged as a logical ring, okay, that you know, and could be unrelated to the physical configuration. Okay, so whatever the process they wants to be enter into the critical section, those process will be arranged as a ring, logical ring. And the PI sends the message to PI plus 1 mod n. That means, see, P1, 2, 4, 5, 6, 7. Okay, so totally 7 process we have. How it is going to be sent? It is going to be sent like this, clockwise direction. Okay. So if this wants to send a message, okay, it should reach again here, then only it will be one clockwise direction will be completed. So each process has an, we can say that each process has an PI, we can say that each process PI has a communication channel to the next process in the ring, PI plus 1 mod n. PI plus 1 mod n, and all the messages are sent in the clockwise direction around the ring. All the messages are sent in the clockwise direction around the ring. Okay. And we can assume that here there is no failure, then the system is a synchronous one. Just assume it. There is no failure. If it is no failure, we can say it is a synchronous. That is, there will be the time bound set or else. Okay. So assume that there is no failure occurs and the system is an, so we can say that, assume that there is no failure and there is a system is an asynchronous one. Okay. And the goal of the algorithm. What is the goal of the algorithm? To elect the coordinator. The goal of the algorithm is nothing but to elect the single process as a, the goal of the algorithm is nothing but to elect the single process that we can call as a coordinator. Okay, which the process with the largest identifier. Okay, next is what? So now this is the goal. Okay, fine. Next, initially every process is a non-participant. I told you, right, all the process is an idle first initially. Okay, and any process can begin the election. Any process can begin the election. Okay, the first one is it proceeds by marking itself as a participant and placing its ID. Okay, the first step is what? Each process is going to be mark itself as an, so the process who wants to, enable the election. Okay, that process itself mark as a participant and placing its identifier in an election message and sending it to the clockwise neighbor. Okay, this means any process can mark itself as a participant. Okay, then after it keeps its message in the election, okay, and sends to the neighbor according to the clockwise direction. Okay, then after, this is what? 3 steps. Okay, now we'll see one by one. That means a ring-based algorithm is a logical ring-based structure, and it will be send one pi sends the messages to pi plus 1 mod n. Okay, and here assumes that there is no failure, then the system is an asynchronous one. And here what is the goal of this one? It will be elect the one process as a coordinator and with the largest ID. Okay, initially all the participants in the, initially every process is marked in a non-participant in the election. Okay, then after any process can begin the election. Any process can begin an election. Okay, so there it needs to be followed 3 steps. 1, 2, 3. How to begin the election? The process itself mark as an participant. Okay, then after it will be keep the place its identifier in the election commission. Like it will be keep its ID. See how the people will be participate in the election. First the participant will be announces that he is a participant, he is going to be participate in the election. Then after he will be give his identifier that will be submitted to the election commission. Then the election will be started along with that, with the help of that identifier. Same like here. Mark itself as a participant, and next one places ID in the election message and sends a message to its neighbor. One is receiving a election message. Receiving an election message. How it will be receiving an election message? I told you, right? If, for example, participant 1, okay, it is having an ID of 32 or something. Okay, so that is going to be circulate. For example, see here, P1, P2, P3, P4, P5. Okay, this is the one which is going to be sent. Okay, announces as a participant. Okay, so its ID is 7, 8, 2 and 70. Okay, now, so this is a neighbor. Okay, so once it comes here, passes to the neighbor. Okay, so this is nothing but my ID. This process ID we can call it as a my identifier. The participant ID is ID. Now you know what is ID, what is my ID. Okay, fine. If ID is greater than my ID, if this one is greater than this one, okay, here the value is what? Only 7. If this is greater than this one, okay, then forward the message and mark as a participant. So this one will be, then if it is greater than this one means it will be forward to the next neighbor. Okay, the next one is if it is less than, that means, for example, this is 70. Okay, that means this is less than, ID is less than my ID. ID is less than my ID. That means 32 is less than 70. Okay, what will happen? Non-participant replaces ID with my ID and forward the message as a marked participant. But here this is a participant and this is non-participant, right, initially. Okay, then what will happen? This, if it is less than this one, this ID is less than my ID. Now this process P2, okay, replaces this ID as, ID value as 70, replaces ID as with my ID, that is my ID 70. Okay, then after that will be forward the message like a participant. Now this is a participant. Okay, and the participant is what? This already the initial participant is stop forwarding. Why? Because it is stop forwarded here itself. Okay, later the multiple elections, maybe after that the multiple elections may be enabled. Okay, if both are same, for example, here it is coming, okay, but all unique process, say again it is rotating in this direction, here both are same, 70 is equal to 70. See, initially this is also lesser, this is also lesser, this one also lesser. Okay, and while coming here, these both are same. Okay, then we can say that this is a coordinator found. Next, receiving an election message. Okay, if ID is not equal to my ID and the marked participant and elect of ID is equal to ID and forward the message, same thing. Okay, if it is not equal to, okay, for example, initially it is a participant, okay, and it is forwarding here up to here, and while coming here, and this will be a participant, okay, and now 86 is forwarding here and 86 coming here, and here also it is 86. Okay, see here now which is initiated beginning, so it is not equal to. Okay, what will happen? Then it will be a non-participant, it knows that, then it will be forward here and again it will be reached here. Once it reaches the same position, that is 86 is equal to 86, then this will become the coordinate. Stop forwarding and make it as a coordinate. See here, initially in this diagram, this process is the coordinate, participant. Okay, and this is the participant. Here what is the value? Identifier number 17, and 17 is forwarding here. Okay, so now this is ID and this is my ID. Okay, well, comparing this one, this is the largest and replaces this my ID with ID now. Now your ID value is 24. Okay, and forwarding here. This is smaller. Okay, fine. And it is coming here, but this is highest. Now, this is the ID now. Okay, why? Because this is largest than 24. And coming here and move, and everything is smaller. Okay, and here is also, it is 28 now. So both are not equal, and again forwarding here. Here also it is a participant, and here also not equal, and coming here. Why? Because we have 3 participants, right? That's what we need to be check in this 3 position. Okay, whether the equal to or not. Okay, so and here also, here not, and while coming here both are equal, and now this is the participant. Sorry, this is the coordinate. Right? What's the property here? Safety and liveness. Yes, this one is achieved. Why? Because only one process become the coordinator and enter into the critical section. Okay, the who is become the coordinator, that is going to be enter into the critical section. So this is satisfied. Liveness is what? Yes, obviously it is going to be asked all the remaining process in the system whether they are going to be entered into the critical section or not. So this is also, so okay, when coming to the performance, okay, here we have only one election in the best case. One election in the best case. Okay, that means how many election messages will be we have n election messages. We will get n election messages. Okay, in the best case I am telling, we have n election messages and the n elected messages, n elected message and the n election message. For example, if you have 6 process, because at a time itself it is selecting. Okay, that means one best case of only one election. Okay, only one process going to be electing, enable the election. Okay, fine. Then after, what will be the turnaround time? Turnaround time is also same. Why? Because only one process. So getting the time between the process entered into the section, the election started and it is going to be terminated is only 2. So 1 plus 1 it is 2. One message and one message. So it is going to become 2. Turnaround time is 2. Okay. Then after, if we go for one election in the worst case, only one election, and that should be in the worst case. If only a single process starts an election, okay, if and only a single process starts an election, then the worst performing case is when its anti-clockwise neighbor has the highest identifier. When the anti-clockwise, for example, see it's rotating like this, right? Okay, but this is P1, this is Pn, this is having the highest. That means it needs to be check all. While coming here again, see after it reaching here again it will need for the another one. Why? Because it's not stopped here. Why? Because this is only initiating. Again it should reach this position and conclude that this is not the participant. Okay, so having the highest identifier, the neighbor, in the anti-clockwise direction. Okay, when its anti-clockwise neighbor has the highest identifier. The total we are having n minus 1 messages here. So previously the best case we have only n messages. Here for elected as well as the election both it's required. N minus 1 messages are required to reach its neighbor. Okay, here n minus 1 messages, here n minus 1 messages required to reach its neighbor. Okay. A total of n minus 1 messages are then required to reach its neighbor, which will not announce that its selection until its identifier has completed on the another circuit. Okay, again what will happen, it takes the further of n messages. Okay, double the time of messages will be required if it is in the worst case. So here I told you, right, turnaround time is 2 into n message, and here the turnaround time will be 3 into n minus 1. Why? Because initially 2 is required, and furthermore again n messages are required. So we need, n minus 1 messages required. So totally 2n minus 1 plus n minus 1 totally which required 3 into n minus 1 messages in the turnaround time. Entry as well as, elected as well as the response election. Okay, both time between the election and the elected. Okay, fine. And we'll go for the failures. Okay, that means it can't tolerate the failures. Why? Because it's not a practical one, because an example of the ring based algorithm in the progress that we shown, here the election message concurrently contains 24, but the process 24 will be replaced the 24 with its identifier. Why? Because this is having the highest identifier. That is having the highest. So we see the previous example, right? So 28 replaces to 24. Why? Because which is having the highest identifier. Okay. Here with a reliable failure detector, if you can say take a reliable failure detector, the principle possible to reconstitute the ring with the process crashes. Okay, if it is a reliable failure detector, means what will happen? The principle, it's possible to reconstitute, or else we can say that reconstitute the ring whenever the process crashes. Whenever the crashes occurs, if it is a reliable system, it will be reconstitute the ring based system. That's all about the ring based system. Next one is Bully election algorithm. The previously in the election, the ring based algorithm, we told that there is no crashes at all. We won't get the crashes. But the Bully algorithm, there is a possibility of getting crashes always. Okay, that is, it allows a process to crashes during an election also. So this will be assumes that the message delivery between the process is reliable. The message between the process are reliable. Just assume. Okay, assume that the message between the process are reliable. Why? Because here we have there is a possibility of crashes while the election is taking care of. Okay, like unlike the ring based algorithm, this algorithm assumes that the system isn't synchronous. Okay, and also it uses the timeouts to detect the failure. What is the timeouts importance? Timeouts means it is going to be detect the failure. Why? Because this is going to be take a synchronous. Previously that system taken asynchronous. Here this system is going to be take the synchronous, and it's going to be detect the failure. Why? Because here there is a possibility of the process may be failed during an election. Okay. Another difference is that ring based algorithm and compared with this one is the process have the minimal prior knowledge of one another. Another difference we can take is the ring based algorithm. It is having each and every process having the minimal knowledge. Okay, minimal knowledge of the between the one another. For example, 5 systems or 5 processes are there, means they don't have that much knowledge of the another process. This process doesn't have the knowledge on these two. Why? Because while coming here only, this process knows the identifier value, which is the participant. That time only they are comparing. Before that, this process couldn't know what is the identifier of the remaining process. Okay, if they know previously, then there is no worst case at all. Okay, worst case what we seen actually in the election algorithm, ring based algorithm. If in the anti-clockwise the neighbor which is having the largest identifier, then the turnaround timing will be more. Okay, that's what the the ring based algorithm, it doesn't have the prior knowledge of the one another. They knows only about how to communicate with its neighbor. Okay, the ring based algorithm knows only how to communicate with its neighbor, and none of the process knows is identifier of the other process. Okay, only their identifier only they know. But while coming to the Bully algorithm, each process knows the remaining process identifier in the system. Okay, which is having the largest identifier also they know. Okay, and they can communicate with along with that information only, the process is going to be elect the participant as the, along with that information because all the process know the identifier of the remaining process, right? So each process knows the identifier of the remaining process in the system. Then for that, with the help of those information, those knowledge, the process is going to be initiate the election. Okay. See here, have the highest identifier, who is having the higher, and it's communicate with the such process. And compare with the ring based, what are the things we see? The crashes will be there and it can be detected by the timeouts. It will be detected by the and it's a synchronous one. And here the timeouts. Okay, that is going to be calculated with the formula 2 into T transmitting. There is a maximum transmission delay plus a maximum processing delay. The timeouts is going to be calculated with this formula. We have 3 types of messages here. One is the election message, another one is answer message, and another one is coordinator message. Election message, answer message, coordinator. Okay. Election. What do you mean by election? The election message is sent to announce the election. It's going to be announce an election to the remaining process in the system. Okay. And answer. The response, the process who are all not elected. Okay. Non-participant. They're going to be send the response to the process which is elected. Okay. That means sending the response to the election message. Sending the response to the election message. And the coordinator. What is a coordinator? Coordinator is nothing but it announce the identity of the elected process. It announces the identity of the elected process and tells that it is a new coordinator. Okay, so these are the 3 types of messages in the Bully algorithm. See, now we'll see this diagram. Okay, see first one, stage 1. In this stage, see totally we have how many processes? 4 processes are there. Okay, that time this P1 is having the highest identifier when compared with the remaining 3 processes. So after it knows that it is going to be start the election. Okay, that means it sends the. So during that time itself, this process P4 crashed. So that which is having the, because all the process knows. Okay, the process which is having the highest identifier only knows that which process crashed. This is one constraint. Okay, not all the process knows this one. Only the process which is having the highest identifier, that process only knows that which process crashed. Okay, so P4 is crashed, so it knows that. So it is going to be send the elections to the remaining 2 processes. Okay, this is the first stage 1. Well, coming to stage 2. Okay, then after that these 2 are answering. What are they? P2 and P3 are answering to the P1. Okay, simultaneously, okay, P2, P3 is also electing. Enable the election. They also want to become the participant. P2 and P3 also wants to become the participant. Okay, so see here, because these 2 processes don't know that P4 crashed, because that is not, so this is only having the highest identifier. Okay, so these 2 processes don't know that, doesn't know that P4 crashed. So these P2 and P3 send the elections. P2 is sending to P3 and P4 and P3 is sending the P2 and P4. Okay. So here P3 answered to P2. P3 answered. Okay, even they answered. Okay, answered means what? They are telling that okay, you enable the election. You become the participant, but still the coordinator is not chosen. Okay, that is what the answer. Okay, sends a reply to those messages. Okay, but in this position, P3, see here, P3 doesn't get any response from P4 until it waits. And one more constraint is there. if they are not getting response from any processor, and that time also the process thinks that, assumes that okay, no other process responding, then they itself assume and they'll become announce that become the coordinator. Okay, so in that cases, this P3, okay, assumes that there is no reply from P4 and P2. So because this one get the response from P3 and it is waiting for P4, but P3 not even getting response from both. Okay, then assumes that if only none of the process is answering, only that time only the process can assume and think that no other process there, so it will become a coordinator. Okay, so this want to become the coordinator, announce to become the coordinator now. Okay, and the stage 3, so before going to announce that P3 is become a coordinator, and that is also crashed. P3 is also crashed now. Okay, and this P2 is also waiting, P1 is also waiting. Response, see, P1 is waiting the election message from these two, and P2 is waiting for P4. Okay, let's see, these two are waiting. But while comparing with P1 and P2, this timeout is larger. This timeout is larger. Okay, so eventually after that, so this timeout, so this will be removed. Okay, then now P2 will be the coordinator at the last stage. So this is what the Bully algorithm. What do you mean by Bully? Actually, that you know, right? If more than, simultaneously more than one process, they wants to become a participant, they are going to be fight. That is what the name called a Bully algorithm. Okay. And here also we have two properties, but here we couldn't say that it is always safety. Okay, if only one process are going to be, we can say why, because only one coordinator that we are going to be choose. Okay, but anyway, none of the that we seen, right, P3 itself assumes that it's going to become a coordinator. That time we couldn't say that this is going to be satisfied. So safety requirement is not going to be satisfied. Obviously, if it is not satisfied, and liveliness is not also, because here they are not going to get any request or response from they are not waiting for any request or response. Okay, why? Because if this is not satisfied and this requirement is also not become satisfied. And here also best case, worst case and turnaround delay will be there. Okay, best case means what? All the process initially it should choose a coordinator. Okay, if you go for the worst case, that is what we seen, that example is nothing but the worst case. Okay, in worst case P2 become the coordinator, right? And the turnaround delay will be there here. Why? Because because of timeout, that first P1 it will be removed from the election, right? The same thing, the turnaround delay is more here when compared with the ring based algorithm. Turnaround delay, it takes order of n square. Okay, so it is more than any other algorithm that we seen previously. So this is the highest turnaround delay. The name itself, they are like a fighting. Each and every process needs to be fight to become a coordinator, right? So this is what the worst algorithm when we seen with the ring. So ring based is the best when compared with this one. But in some cases, even though they know the information between the neighbors, okay, but we couldn't satisfy, it is not satisfying the two properties, the first two the requirements in the properties. Okay, that's all about the Bully algorithm.